The first method is principal component regression. Principal component regression. So to understand the principal component regression technique, we have to understand what is principal component of your input data. Okay, so what is principal component? At first, we have to standardize all the matrix X, the column of matrix X. So what was matrix X? X was the matrix consists of your input predictors, so x1 transpose, x2 transpose, and so on up to xn transpose. So the shape is n by p matrix, and let's say X matrix consists of p columns denoted by x1, x2 up to xp. Okay, so the principal component technique usually at the beginning standardize the columns. The standardized column means make the column having to have mean 0 and variance 1, which means make xij equal to 0, I is 1 through n, and also make the square equal to 1. How to do that? Basically, we can redefine xij using the empirical mean and empirical variance, which is the very standardized process for the. Sometimes it is called data pre-processing. In many machine learning applications or in many machine learning algorithms, when you do standardize at the beginning, usually the performance can be better than before. Okay, so zero mean at a unit variance input shape is very nice for training your machine learning algorithm and for the inference task as well. Okay, and using the standardized columns, at the second step, we extract the principal component of your input matrix X. So what is principal component? The first principal component is argmax pi vector such that the two-norm is equal to 1. Of course, the pi belongs to p-dimensional space. X times pi two-norm is minimized. So we want to find the unit vector pi that maximized the x times pi norm. Okay, so this is called principal component from the right hand side. You can define the same principal component from the left hand side of your matrix X. So let's say Z1 is the first principal component from the left hand side. Then this is argmax Z vector such that the rank sub z or 2 norm of z is equal to 1, and of course the z vector belong to n-dimensional real space, and that maximize z transpose x 2 norm. So this is the first principal component of matrix X from the left hand side. Okay, so this is the first principal component. You can define the second principal component as well. Like before, this is argmax pi having unit ranks, and of course this should be belong to p-dimensional real space, and then maximize x times the pi vector, then which will give you the same vector with the before. So the result will be the pi 1. So the second principal component has another constraint. This should be orthogonal to pi 1. Orthogonal means the inner product between pi 1 and the pi vector should be equal to 0. Okay, so the second principal component means is a unit vector that maximizes the length of x times pi from the constraint set or constraint space that is orthogonal to the first principal component. Okay, Z2 as well. The left-hand side principal component also defined in the same way, equal to 1. Z belong to n-dimensional space, and Z also orthogonal to Z1, the first principal component. How about third principal component? This is again the same. Argmax pi, the ranks is equal to 1. This should be orthogonal to the first principal component. This should be orthogonal to the second principal component as well. Of course, it belongs to p-dimensional space, and then maximize x times pi from the constraint space. Z3 as well. Okay, so you can define principal component in this way as many as you want. Right. So the principal component of regression task is basically define a linear regression task using a new parameter theta 0 plus G1, G2 second principal component, third principal component up to m's principal component from the left hand side, and product with the new m parameter theta 1 through theta m plus noise, plus observation noise or the model noise. So then the residual part. So and then train theta 0 and theta 1 through theta m that minimize the RSS objective function. Okay, so here G1, G2, G3 up to Gm, they are principal components of your data matrix X from the left hand side. Okay, and here basically when you compute the Z1 through Zm, there is a matrix A definitely then make the G1 through Gm from x times A. Okay? So when you have a new observation, then from the trend parameter theta 0 and theta 1 through theta m, you can make the prediction of your new input from theta 0 plus x transpose times A in a product zeta vector. So this is your new prediction, which consists of n plus 1 parameters, which is less than p plus 1, the original linear regression model. And you can control the number of parameter m from the deciding how many principal components you will use to define this linear regression task. Okay, and here the A matrix basically is equal to the sigma inverse and pi 1, pi 2 up to pi m matrix. Okay, so what is the meaning? I will explain. So this principal component essentially has a very directly used extracted from singular value decomposition. So what is the singular value decomposition? For any given matrix X, you can define a singular value decomposition consists of 3 different components. This is the singular vector matrix, left-hand singular vector matrix U, singular vector matrix U, singular value diagonal matrix sigma, and this is right-hand side singular value singular vector matrix V transpose. Okay, then what is the meaning? U transpose times U basically is identity matrix, and V transpose V matrix also identity matrix, which means the U and V matrix are orthonormal, which means the columns of U matrix and the columns of V matrix are orthonormal. So the length of each column is equal to 1, and if you pick any 2 columns from U, then the inner product between the 2 columns will be 0. The same thing happened for V matrix as well. And what is the shape of sigma? Sigma is the diagonal matrix. So the off-diagonal element is equal to 0, all element. And only the diagonal part has non-zero element. And the diagonal part consists of singular values. Okay, let's say this is sigma 1, sigma 2 up to sigma p, and basically sigma 1 is greater than or equal to sigma 2, and so let's say the singular values on the diagonal part sorted by the values in descending order. Okay, then how can we define the singular values and singular vectors, and how can we construct this singular value decomposition? there are a bunch of algorithms that can extract the singular value and singular vectors. That is out of scope of this class. But if you're interested in how to construct this singular value decomposition, then please search Google. There are tons of nice web pages, and you can understand one of them. And if you have any question on that, I very welcome any questions. So please post anything on our Q&A board or our classroom page. Okay. So why I explain this singular value decomposition? Basically, the singular vectors are principal component. The singular vectors corresponding to the first singular values, so which means the first column of your singular vector matrix U, which is the first principal component from the left hand side. First column of V matrix is the first singular vector from the right hand side. And if you multiply V matrix here, then since V transpose V is identity matrix, so X times V matrix is U times sigma. And so you multiply sigma inverse matrix, and by the way, sigma inverse matrix is just another diagonal matrix with 1 over sigma 1, 1 over sigma 2, and so on, which is basically equal to U matrix. Okay? So because the first column is the first principal component and the second column is the second principal component, so how to extract the first and second principal component from the singular value decomposition? This is very trivial. You just pick the first two columns of V matrix and you just pick the 2 by 2 sub-matrix of sigma inverse matrix, so that in the end you have just the first two columns of U matrix. That's it. So when you do the singular value decomposition, basically you just have the what is principal component and what is the principal component from left hand side, right hand side, everything you need. Okay, the principal component and singular value decompositions are very important concept in machine learning. So we will revisit this part maybe in 4 weeks, I guess. And this is very important information, but the only drawback of singular value decomposition is basically it is very difficult to extract when the matrix size X is very huge. For instance, X is millions by millions, then the running time to extract the singular values and singular vectors are very, very huge. Alright.